Hey everyone, and welcome. So, you've got survey data, and you're thinking, how can I make my estimates even more accurate without having to go out and collect more data? Well, you've come to the right place. Today, we are going to dive into how you can use what's called auxiliary information right inside R to seriously boost the precision of your survey estimates. We'll be looking at two really powerful techniques: ratio and regression estimation. So here's our game plan. First, we'll get the big idea behind boosting precision with data we already have. Then, we're going to see ratio estimation in action with a couple of different real-world examples. After that, we'll switch gears and look at regression estimation to see how it gives us a bit more flexibility. And finally, we'll wrap it all up with a summary of the key R tools you'll be able to use in your own work. All right, first things first. Let's talk about the secret sauce that makes all this work. It's this fantastic concept of using data you already possess to make the new data you just collected way, way more powerful. I mean, this is the million-dollar question, right? We've got our sample, and we want the absolute best estimate for the whole population. But, budgets are always tight, so how do we get more bang for our buck from the data we have?
The answer is something called auxiliary information. Think about it like this. Let's say your variable of interest, your y, is the total weight of all the apples in an orchard. Now, that's hard to measure directly. But what if you already knew the total number of trees in that orchard? That's your x, your auxiliary variable. If you know that more trees means more apples, that they're correlated, then that existing data, the tree count, becomes this incredibly powerful tool for getting a much sharper estimate of the total apple weight. Okay, enough theory. Let's get our hands dirty and see how this actually works inside R using this survey package. We're going to start with some agricultural data about farm acreage. Now, before we write a single line of code, we have to do a crucial check. For ratio estimation to really shine, our variable of interest, in this case farm acres in 1992, has to be tightly related to our auxiliary variable, the acres from 1987. It makes sense, right? If the two aren't correlated, then knowing about one doesn't really tell you anything about the other. And what do we find when we check? Wow, a correlation of nearly 0.996. That is an unbelievably strong positive relationship. It's about as close to a perfect one-to-one correlation as you'll ever see in the real world. This tells us we've hit the jackpot. Acres 87 is a fantastic predictor for acres 92. And if you're a visual person, check this out. This scatter plot shows exactly what that number means. You can see the data points form an almost perfect straight line that seems to go right through the origin, where 0 acres in 87 would mean 0 acres in 92. This is the textbook, A+ gold standard scenario for using ratio estimation. Okay, let's walk through the R code. First, we load our AGRS data. Then, we define the sampling weights. Since we took a simple random sample of 300 farms from a population of 3078, each farm in our sample represents about 10.26 farms in the total population. Next, we create our survey design object with SWID design. We tell it our weights and, importantly, the FPC, the finite population correction. That FPC tells R that our sample is a pretty big chunk of the whole population, which lets it calculate more accurate standard errors. Finally, the star of the show, SV ratio, where we simply tell it our numerator, acres 92, and our denominator, acres 87. And here is what R gives us back. It calculates the ratio as 0.987 with a teensy tiny standard error. So what does this number actually tell us? It means that, on average, the acreage in 1992 was about 98.7% of what it was in 1987 for a given farm. And because that relationship is so stable, we can now use it to make some incredibly precise predictions. So how do we do that? We use the predict function. The logic is actually super simple. We have the official known total acreage for all farms back in 1987. That's our XPOP total. All we have to do is multiply that known total by the stable ratio we just calculated. The predict function does all the heavy lifting, including calculating the correct standard errors for our new estimate. And we can do the exact same thing for the mean, too. And here's the payoff. Our model gives us an estimated total of about 951.5 million acres for 1992, with a standard error of only 5.5 million. Now get this, if we had just used a simple estimate from our sample without using the 1987 data, our standard error would have been almost twice as large. That's the power of auxiliary information right there. We've literally cut our uncertainty in half without collecting a single new piece of data. Okay, so that first example was pretty much perfect. But in the real world, things got messy. So what happens when we face a really common problem? We don't actually know the total population size. Let's check it out with a new data set on Santa Cruz seedlings. So here's the big difference between the two scenarios. For the farm data, we knew N, the total number of farms. For the seedling data, the total number of trees in the population is a mystery. And that unknown N means we have to make a few small but really important tweaks to how we set up our survey design in R.
Just look at how the code changes to handle this. Since we don't know the total population size N, we can't calculate a real sampling weight. So what do? We just set the weight to 1 for every single observation. And because we don't have N, we also can't use the finite population correction, so we just leave out the FPC argument. This basically tells R to act as if the population is infinitely large, which is the standard conservative approach here. But after that setup, the rest of the process, calculating the ratio, is exactly the same.
Now, in this case, the correlation is much weaker, about 0.61. It's still helpful, for sure, but it's not the near-perfect relationship we saw before. Still, the method works just fine. It gives us a ratio of about 0.3, which suggests the number of seedlings in 94 was roughly 30% of what it was in 92. But we should definitely expect our final estimates to be a little less precise than they were with the farm data, and that all comes back to that weaker starting correlation.
All right, let's add another powerful tool to our collection, regression estimation. This technique is similar to ratio estimation, but it's even more flexible. It's particularly useful when that straight line relationship between our variables doesn't go neatly through the origin. Let's explore this using the dead trees dataset. The workflow for regression estimation is also a really clear 4-step process. Step 1 is the same as always, define the survey design. But here's the key difference. Step 2. Instead of calculating a simple ratio, we're going to fit a full linear model using the amazing SVGLM function. After that, we check out our model with summary, and then just like before, we use predict to get our final population estimates. Let's look at the R code. The SVI design function should look pretty familiar by now. The new piece of the puzzle is SVIGLM. Inside, we use this formula syntax, field, shint, photo. That's just R's shorthand for saying, I want to predict the field count of dead trees, and I'm going to use the photo count as my predictor variable. And the summary output is where you find all the good stuff. The intercept, around 5.06, is our model's baseline. It's telling us that even if 0 trees were counted in a photo, our model would still predict about 5 trees are actually there in the field. The photo coefficient, 0.61, is our slope. It means for every 1 additional tree you count in a photo, the model predicts you'll find about 0.61 more trees on the ground. And those super tiny p-values, they just confirm that this is a real statistically significant relationship, not just random chance. Now, predicting with a regression model works just a little differently. We have to explicitly tell R what value we want to predict for. We do this by creating a tiny new data frame that holds the known population average for our photo counts, which happens to be 11.3. We then feed our fitted model and this new data to the predict function. It's like asking the model, hey, can you plug 11.3 into your equation for me and tell me the answer? We then do the same thing to get the total, using the population total of 1,130. Okay, that was a whirlwind tour of 2 incredibly useful techniques. Let's take a moment to recap and distill this all down into the essential R functions you now have at your disposal. So here it is, your new survey estimation toolkit. SPI design is always your first step. It's the foundation for everything. SPI ratio is your specialized tool, perfect for those clean, through-the-origin relationships. SPI GLM is your flexible all-rounder, great for more complex situations. And finally, predict is what brings it all home, turning your ratios and models into the final population estimates you need. And to wrap things up, I want to leave you with a final question to chew on. We've seen how powerful both these tools are, but think about this. When would you specifically choose the regression model over the ratio model? Imagine you have a really high correlation, but when you plot the data, the line clearly doesn't go through the origin. That's a classic case, where the flexibility of SVGLM with its ability to estimate an intercept makes it the superior choice. Thanks so much for joining me.